Hey everybody, welcome to our next lesson, which is on solubility equilibria. Some of you may have seen in some of the notes already subscripts for our K values with an SP there, so KSP. That's what we're going to be talking about today. So solubility equilibria, look at solubility product of equilibrium. So you guys have learned in chapter 7 of the textbook that saturated solutions with undissolved solutes. So that is solutions that have a little bit of the solute at the bottom, sitting on the bottom of the container, is what we would call a heterogeneous equilibrium. So if you've got, I think the example that I gave a couple weeks back was, the Kool-Aid with the water, right? If I keep adding scoops of Kool-Aid, only so much of that Kool-Aid will dissolve, and when it stops dissolving and you can't dissolve anymore, it doesn't mean that the dissolution process has stopped. It just means that the rate at which it dissolves is equal to the rate at which it precipitates out. So we reach an equilibrium there. And you've also learned last year when in grade 11 when we talked about solutions and solubility, that the amount of solute that can dissolve in a given amount of solvent is what we call solubility. So solubility, when we look at it in terms of chemistry, can be expressed using many units. So most of the time we will use in chemistry moles per liter, but sometimes we use other units, things like grams per liter. We can use, if you have really small concentrations, you can look at parts per million or parts per billion and whatnot. What a part per million is, what a part per billion is really simple. So here's a good way to remember it. 1 gram in a million grams represents 1 part per million. If I take this gram and divide it by 1,000, take this million and divide it by 1,000, I get 0.001 grams in 1,000 grams. Well, I can convert this 1,000 grams into kilograms, and I can convert this 0.001 gram, or 1,000th of a gram, into milligrams. So 1 milligram in 1,000 grams, or 1 milligram in a kilogram, is a part per million. Which translates, if we're looking at the density of water and looking at another way to represent it, it's 1 milligram per liter is equivalent to 1 part per million. So let's chat a little bit about heterogeneous equilibria. So consider the salt solution that's made of barium sulfate. I take some barium sulfate, it's a white powder, I drop it into some water. It will form an equilibrium. So when the salt crystals do dissolve, the concentration of the dissolved ion is very, very, very low, and therefore the forward reaction is favored at the beginning. So I have some barium sulfate solid, and it turns into barium ions and sulfate ions in solution. So you'll remember from grade 11, solutions and solubility, that our ions or our salts, I should say, will dissolve into their respective ions. However, as this process starts to proceed more to the right, you reach a point where the rate of the forward reaction, the rate at which it's dissolving, is equal to the rate at which it is precipitating out or recrystallizing. And eventually, when you get those rates equalized, you've reached a new equilibrium. Now, if I were to express this in terms of an equilibrium expression, I know that my KEQ is equal to the concentration of the products over the concentration of the reactants raised to their coefficients. But there's a problem here. One of the problems is that you have this small S value, or S subscript here, which represents solid. So if I were to take a solid and I look at how its particles are distributed, whether I have, 100 grams of the solid or 50 grams of the solid or 1 gram of the solid, the distribution of all of the particles within that solid are equal, which means that solids have constant concentrations. And as a result of them having constant concentrations, this denominator here is a constant. And so if this is a constant, and so is KEQ, if I were to take this BaSO4 and bring it up, like I have right here, then I have a constant multiplied by a constant, which will produce a new constant. And that new constant is what we call KSP. It's the solubility product. So it's, when we say product, we mean multiplication. So it's the solubility of all of the ions multiplied against one another. That's what we call KSP. So when we look at our KSP expressions, we ignore the solid reactant in terms of concentrations because the concentrations remain constant. We only look at the concentrations of the dissolved ions. So let's look at a sample problem here. They're not too difficult to solve. So it says calculate the solubility product if the solubility of silver carbonate is 1.3 times 10 to the minus 4 molar. Big M, remember, is moles per liter. So I've set up an expression here. I've got my silver carbonate. It's going to dissolve into silver ions and carbonate ions. If I know the concentration of this, I take that, 1.3 times 10 to the minus 4. I can tell you what the concentration of my individual ions are. So notice that there is a 1 to 2 ratio for silver ions. So every time one of these particles dissolves, I get 2 silvers and 1 carbonate. So if that's the case, then for every one of these that's dissolved, I get 2 of this silver, and so I have a concentration of 2.6 times 10 to the minus 4 moles per liter. You'll also notice that it's a 1-to-1 ratio between the silver carbonate and the carbonate ion. And so if it's a 1-to-1 ratio, I have the same concentration. And then all I need to do is take the concentrations of my individual ions, as I've shown you right here, and multiply them across, of course, raising to their coefficients. So it's 2 silvers, so it's concentration of silver squared times the concentration of carbonate to the power of 1. And then I just take my values that I've calculated here and I plug them in. So 2.6 times 10 to the minus 4 squared times 1.3 times 10 to the minus 4 gives me a KSP value of 8.8 times 10 to the minus 12, which is a really small number, which means that my solubility product, because it's so small, means that not a lot of the barium sulfate will dissolve at all in solution. So let's look at a separate problem, one that requires an ice table. So it says here at 25 degrees Celsius, the solubility product of lead iodide is found to be 9.8 times 10 to the minus 9. So I want you to think about what that means, right? It's a solubility product. So it's giving you in the question a KSP value, and it's asking us to determine what the molar solubility of lead iodide is in the water. So I want to know what the value of X is here. Now remember over here, I gave you the values of X. Down here, we have to figure out what those values of X is. And then it's asked us, not only for us to calculate the molar solubility, so it's asking in moles per liter, but I also want it in grams per liter and in parts per million. So let's go through how to do that. Well, I would set up, of course, my ice table. Here's my equation. So I've got lead, iodide solid turning into lead ions and 2 iodide ions. I don't have any initially of my lead ions or my iodide ions, so we have zeros there for my initial. You'll also notice that there are dashes here. There's dashes here because this is a solid chemical here, which means it's got a constant chemical concentration. So we don't have to worry about it changing because it's not going to ever change. So we just ignore that piece as I showed you the derivation of the KSP formula. When this starts to dissolve, we know that for every 1 lead iodide we're going to produce 1 lead ion and 2 iodide ions. So this one is going to increase by a factor of X. That's why we have a plus X here. This one's going to increase by a factor of 2X. And then, of course, 0 plus the 2X produces a 2X value at equilibrium here. 0 plus X produces an X value here. And so when I actually start to substitute things in, I know that my KSP value is 9.8 times 10 to the minus 9. That was given in the question. That is equal to X, which is this one, to the power of 1, which of course we don't write that power of 1, times 2X, notice the equilibrium concentration here, 2X to the power of 2. So 2X squared is 4X squared, times another X gives us 4X cubed. And then I can actually determine this very easily. So I can take the 9.8 times 10 to the minus 9, divide it by 4. So I'm going to take the 4 from here, put it over to the other side, divide by 4, and then take the cubed root of it, and I'm able to determine my X value, which ends up coming out to 1.35 times 10 to the minus 3 moles per liter. So that value here is our molar solubility. It's the value of X here. Remember, we have a 1 here, so we know it's equivalent to X. So this is how much will actually dissolve into solution of this lead iodide. But of course, the question asked us to also convert it into grams per liter and into parts per million. So in order to go from a moles per liter, a molar solubility, into grams per liter, I need to take the molar mass of the substance and multiply it by the concentration of that substance in moles per liter. And of course, when you do that, the moles on the top in terms of the concentration will turn into, will cancel out with the moles on the bottom and produce grams over liters. And so I end up with a concentration in grams per liter of 0.62 grams per liter. Now, you'll recall earlier I showed you guys how to convert between grams per liter and parts per million. And so we know that the equivalent value of 1 parts per million is equal to 1 milligram per liter, or 1 milligram per kilogram. Now we are measuring everything in liters here, so 1 milligram per liter. Well, 0.62 grams is equivalent to 620, so these two values are equivalent. It's equivalent to 620 milligrams. So there are 1,000 milligrams in every gram, so 0.62 grams has 620 milligrams. We know 620 milligrams per liter. We'll look at the units here. Milligrams per liter equals parts per million. And so I end up with 620 parts per million. So if I had a million particles of that solution, 620 of that million would represent my particulate that's dissolved in my solute. So those are how you calculate KSP problems. So you'll get one of each of those types likely on a test. So yeah, that's pretty much it. If you guys do have any questions, send me emails and I'll be happy to help you guys. Thanks, guys.